Well, let's consider the curve given by that equation. It can be shown that the derivative is this. That would involve implicit differentiation to go from here to here. They did it for you, so you don't have to do it. Lucky you. Great. Now, sometimes they'll say, consider that. It can be shown that. And then part A will say, demonstrate that the derivative of this is this. And you kind of have to walk through that process. They didn't, though. Here goes. Find the equation for the line tangent to the curve at the point -1, 1. Okay, great. Well, I know how to find the equation of a line that is tangent to a curve. If I want to find the equation of a line tangent to a curve, then I need three things. I need an x, I need a y, and I need a slope. So let's just jump right into it. So here goes. 6a, y minus y1 equals m, x minus x1. And I'm going to go ahead and just plug in everything I know, and we'll go from there. Since I know the coordinate -1, 1 is on this curve, so we'll do this. I'm going to leave that m blank. X minus -1. There we go. And then, dust all over my paper. And then I want to find out what the slope is at that point. So I'm going to evaluate dy dx at a specific point, and I'm just going to show it like this, -1, 1. You've seen this vertical line before in a different context, but that's just my way of saying I'm going to evaluate this here. It's mathematical notation, fun stuff. So that means I have 1/3 times 1 squared minus -1, and that gives me 1/4. By the way, that number is going to come in much handier later, but there we go. And we actually found the equation of the line. You could leave it like that. I'm going to go a little bit further, and I'm going to do 1/4 x. The more you do, the more room for error there is. Actually, the answer key says this. I'm going to leave it like that, and that's perfectly okay. You probably could have left it like that as well. So you get a point for the slope, and you get a point for the actual equation for the tangent line. So let's move on to part B, which says, this one's tricky. Find the coordinates of all points of the curve at which the line tangent to the curve at that point is vertical. Okay, well, if I have a vertical tangent line, then we've got this thing going on. Looks like that. A vertical tangent line has a slope that is undefined. Well, an undefined slope means the denominator is 0. So here's what's really going on. My denominator, there's my slope, obviously, is equal to 0. And when I first did this one, I looked at it and I thought, well, you know, I don't know how to solve. Like, there's two equations and one variable. So two variables in one equation. So, like, what am I solving for? And I want to find all the coordinates. So what I started doing, and I can kind of show you my work, but I started kind of going through all this, and I isolated the y, and I got here, and I thought, this is really getting me nowhere. And then it dawned on me that what I can do is take the other information that I have, and here it is. I know this is true, and I also know that this is true. So why don't we take this idea and solve for the obvious variable? We'll solve it for x. Obviously, solving for y would give us that plus or minus square root, and it's just not going to be worth our trouble. But we'll also take that, and we'll go in conjunction with this that they gave us. And so when you hit a roadblock, like I did when I was doing this one, you start thinking, well, what do I know, and how can I use it? So what I'm going to do is just basically take this that I was dealing with and solve it for x, and then plug it into that one right there. So y cubed minus 3y squared times y equals 2. And so I have y cubed minus 2y cubed equals 2. 3. Sorry, I was getting ahead of myself. So -2y cubed equals 2. So y cubed equals -1. So the cube root of -1 is, well, -1. And now I can find out the actual coordinate. And that coordinate will be, well, let's plug a -1 back in here. So 3 times -1 squared equals x. So x equals 3. And so I'm going to write it as a sentence just because I want to put it in context. So the line tangent to the curve, tangent, I'll spell it correctly, to the curve is vertical at the coordinate 3, -1. All right, and then we get to part C, and that's where things get a little bit interesting. Before we get to part C, let me show you how they graded it. They wanted to see that you set that denominator equal to 0. They wanted to see the equation in one variable, meaning that at some point you got it down to one variable like that, and then the actual coordinate right there, just that one coordinate. That was the only one. All right, part C. This one's going to be worth 4 points. Every free response is worth 9 points. We've had 2 here, we've had 3 here, so this one had better be worth 4. And part C says, evaluate the second derivative at the point of the curve where x equals -1, y equals 1. So the same coordinate, but now we need a second derivative, and this is going to get tricky. Not that we don't know how to do it, it's just that there's a lot of room for error. So we have to be very careful. So dy dx, I'm just writing it again, and that might be a waste of your time to do so, but I'm doing it so I can kind of look at it and see what I need to do with it and point at it as I explain things. So here goes. There is the original derivative. And now we're going to find the derivative of that. So this is going to involve the quotient rule. So FG. So f prime, the derivative of y, is dy dx. F prime, oops, got ahead of myself, g minus f, and then g prime. So the derivative of all this, that would be 6y dy dx minus 1. F prime g minus f g prime, all divided by g squared. Sorry, all divided by g squared. There we go. I'm writing crooked. It's kind of going up. And we want to evaluate this at the coordinate -1, 1, because that's what they told us to do. So if you're thinking like I originally was thinking, then you might say, well, why don't we take dy dx out and we'll put this in its place? I'm going to go ahead and tell you that is going to complicate your life all kinds of ways, because you're going to have y over 3y squared minus x times 3y squared minus x. Those would cancel. Minus y, 6y, y over 3y squared minus x minus 1 over, my word, you got a mess. Don't. Here's this beautiful thing that's about to happen. I want to evaluate this at the coordinate -1, 1. And when I do, I'm going to plug in -1 for every x and 1 for every y. However, this is the same coordinate that was already evaluated at the derivative up here. So everywhere I see dy dx, I'm going to put 1/4 because I've already evaluated it. So I have 1/4. And then 3y squared, I'm going to leave some things out, 3 times 1 squared, and then minus -1. Some of this can happen in your head, clearly, but I've already skipped a lot of steps in my head. So minus y is 1. Times 6y, 6 times 1 times 1/4 minus 1, all divided by 3 times 1 squared minus -1 squared. And then we just do the math. So we have, writing too many steps here for a BC student, 1/4 times 4, duh, minus 3/2, that's 1.5. Minus 1, that would be 1/2. All divided by 4 squared, that'd be 16. So we're going to have 1 minus 1/2 over 16. Again, do as much of this in your head as you feel necessary. Just be very careful. Don't lose track of what you're doing. 1/2 divided by 16. If we double the numerator, double the denominator, we'd have 1 over 32. Okay, let's see how they divided up the points. Implicit differentiation was worth 2 points. I don't know if they separated those 2 points, but basically this right here was worth, well, 2 points. So you got 2 points for all that right there. That's why I drew 2 arrows. Then if you substituted for the dy dx, that was another point right there. So you could have used direct substitution, like this goes in the place of dy dx, or you could have used the 1/4. Either way, same answer. And then final answer of 1 over 32. That was the final point that you get for that one.